Great. Very honored to be the first one to present. So today I'm going to present my proposal, a multi-layered dynamic security framework for DeFi smart contract. So I'm Zhiyang Chen, third-year PhD student at University of Toronto. First, I need to introduce some background. What is a smart contract? A smart contract is a self-executing program on top of blockchain, and users and contracts can interact with a smart contract by issuing transactions. And once deployed, the code of a smart contract is immutable. And a contract accumulates a history of transactions. The transaction history records all the past executions, and they're all publicly available on the blockchain. So one of the most successful applications of the smart contract is decentralized finance, DeFi. For example, yield earning protocols in DeFi can automatically distribute users' tokens to other DeFi protocols to maximize the users' returns or interest, but they need information such as Oracle prices from off-chain from external smart contract. And one very unique property of smart contract is composability. So DeFi smart contracts work like Legos. For example, in DeFi Protocol A, consisting of 4 smart contracts. These contracts are built on top of some other smart contracts, such as oracles or other DeFi protocols, and these other DeFi smart contracts serve as the infrastructure of the DeFi and allow anyone to build on top of this. In today's blockchain industry, the life cycle of a smart contract typically looks like the following. First, developers implement the smart contract. They send it to a security auditing company, which runs a variety of tools in academia or industry: static analyzer, symbolic execution engines, or fuzzing tools to detect vulnerabilities. They report the high-risk vulnerabilities back to the developers, and if there's no other critical issues or all the vulnerabilities has been addressed, the developers will continue to deploy the contract on-chain. And from that point onward, it becomes immutable. The smart contract may function well for some time until one day it got hacked. In such cases, maintainers can do some emergency stop, such as trying to send a transaction to pause the protocol before the attacker's transaction hits the blockchain, but if that fails, which is very common, the funds are stolen, and there's nothing more can be done after the hack transaction are finalized on-chain. So if you look at this life cycle, the current model relies almost entirely on pre-deployment auditing. If a vulnerability slips through the auditing and no white hack discovers the vulnerability before the hacker, then it's effectively game over. So my proposal here aims to add an orthogonal defense layer that complements the existing lifecycle to protecting smart contracts from its deployment to its exploitation. So the intuition behind this proposal is what we observe: the usage of DeFi protocols can be very different for benign transactions and hack transactions. Let me give you an example to illustrate that idea. So for instance, consider a very simple benign deposit transaction. A user deposited 1,000 tokens into DeFi Protocol A, which then deposited these tokens into some other protocols. And that's it for a very simple deposit. For withdrawal, after some time, the user requests to withdraw their tokens. DeFi Protocol A retrieves these tokens from its underlying other DeFi protocols, queries an oracle, and to track the current price of user deposit, and finds that the user's original deposit has accrued some interest. Consequently, the user receives 1,025 tokens, which is the original deposit plus some interest. However, what will a hack transaction look like? It looks like very differently. For example, in an oracle manipulation attack, in one transaction, a hacker can deposit 1 billion tokens into DeFi Protocol A. DeFi Protocol A, as before, deposited this 1 billion token into some other protocols. And the attacker then manipulates the Oracle smart contract by donating a lot of tokens to inflating the prices of the tokens inside that Oracle. Then the hacker attempts to withdraw it from the DeFi Protocol A, As usual, the DeFi protocol A withdraws tokens from its underlying DeFi protocols, but this time, due to the inflated price of the oracle, it wrongly calculates the token amount. Now the user can withdraw 2 billion tokens back. Consequently, the attacker is allowed to get back 2 billion tokens. This is clearly malicious and significantly different from the benign transactions, both in terms of the scale of the numbers, but also the action sequence. So the bottom line here is the DeFi protocol A cannot fully trust its users. It cannot fully trust other DeFi protocols or oracles. Despite the lack of the complete trust, DeFi protocol A must still rely on them because they represent the fundamental infrastructure of the DeFi ecosystem. So building without using this infrastructure DeFi Legos would require an impractical amount of engineering work to rebuild the whole DeFi world, which is not possible. So a practical approach here is to mitigate this issue by safeguarding smart contract with these safety guards. These safety guards are inserted in the source code of DeFi protocol A, trying to guard DeFi protocol A against all the unreliable external dependencies. It can, including the users, oracles, and other DeFi protocols. Additionally, it involves performing internal health checks for each transaction to ensure the protocol remains in its healthy state. In practice, these checks are implemented using the guards, assertions inside the code. But wait a second, you just mentioned the after deployment, the smart contracts are immutable. How could you still instrument those safety guards? Yes, but there's a new design named upgradeable smart contract, which separates the storage state of a smart contract from its implementation logic. So in that case, it allows the proxy contract stores the storage slot, while the implementation contracts have the logic, which can be changed by updating the address of the implementation smart contract. All right, with that new design, here we propose our first layer of defense, which is how to instrument one single smart contract with runtime invariant guards for preventing the hacks. So these guards check safety properties during execution and will revert the transaction when the property is violated. To further illustrate the significant difference between a benign transaction and a malicious transaction with respect to one single smart contract, let's look at a real-world example here, the Harvest Finance hack. We collected all the transaction history data from the Harvest smart contract and measured them in terms of the access frequency, the token flow, gas consumption, and values of special parameters. We find the last data point, which represents the hack transaction, consistently stands out as an outlier in the entire transaction history, highlighting the significant difference between a malicious transaction and a benign one. With this big difference, can we do something to stop the hack? Actually, the developers are already starting to do it. So in a smart contract programming language such as Solidity, developers can actually insert the assertions statement into the code to check the contract state on the fly. However, before this work, there was no research of which invariants are most effective against known DeFi hacks, and how to choose the parameters inside the invariant is also not systematically investigated. So we conducted a qualitative study on the audit reports and source code of 63 audited projects from consensus from 2020 to 2023, and we collected over 2,000 invariants and categorized over 800 invariants into 8 categories. We find the 4 categories: access control, time lock, money flow, and data flow actually covers 94% of the all invariants categorized. Next, we are going to introduce the selected smart contract invariants in the money flow and data flow categories to give a brief overview of how it works in reality. So first one is money flow category. This one is called the token amount upper bound. This is actually very simple. It basically limits the amount of tokens that can be withdrawn in one single transaction. Every time a withdrawal is attempted, it ensures that the amount withdrawal does not exceed a predefined bound. And for the data flow invariant, it's an extension of the money flow invariant. The amount of tokens a user can withdraw is actually calculated based on several values, including function return values and some bookkeeping data inside the smart contract. The data flow invariant sets an upper limit on each of these values used to calculate the withdrawal amount, ensuring the withdrawal remain within the safe bounds. We implemented a tool called trace-to-inv, aimed to infer the invariant from transaction history and concretize the undetermined parameters within the invariant template. Here is our framework and an illustration of our tool. Given a historical transaction, which is a list of the opcode, we crowd the raw trace of it, and then we extract its invocation tree from the raw opcode trace. And from this, using these execution trace snippets, we apply different techniques depending on the type of invariant, such as invocation tree analysis, type inference, or dynamic tint analysis. To extract invariant-related data, each invariant type requires different data extraction methods, and we also deploy different heuristics to determine the parameter within this template. Ultimately, we obtain all the applicable invariants for each function, and we apply this invariant as safety guards to test it against the hacks which already happened. And here is the effectiveness for our tool. We find the trace-to-inv and these practical invariants are actually very effective. The 4 most effective invariants can already prevent more than 85% of the hacks, with introducing a very low false positive rate. And if we combine them with conjunction and disjunction, they can even have a lower false positive rate with a higher true positive rate. We also compare it with the state-of-the-art invariant mining tools or the state-of-the-art attack detection tools, and we surpass their performance both. Okay, next, let's move on to the next line of defenses in our system. So if you look at the first layer, it has a very big drawback. It needs transaction history to learn the undefined parameters inside the invariant templates, which means it cannot be deployed immediately after the deployment of the smart contract. So here's a question. Can we find a better way to safeguard the smart contract right at its deployment? What if we can instrument a smart contract only once at the deployment and have that instrumentation protected from the beginning to the end of its execution? You may wonder whether it's possible. Yeah, let's see if it is. We begin by examining control flows. Here's a surprising empirical finding. In most DeFi protocols, the vast majority of the transaction has trivial control flows. In other words, the transaction invoke only one function. The user only invoke one function. Take Uniswap, one of the most widely used DeFi protocol as an example. Here in the second diagram, the orange bar represents the trivial invocation, the trivial control flow, and the blue bars represent non-trivial ones. So if we have a line up there, we can find even for Uniswap, the non-trivial control flow account for only less than 1% of all the transactions. And for other less popular protocols, the fraction is even smaller. We also conduct even very large scale on the control flow of the hacked protocols. We analyzed the 33 hacked protocols from 2020 to 2024 using Etherscan labels to identify the contracts belonging to each hacked protocols, which crowd all the transactions over 200K transactions with this of these target contracts and extracted their control flows. A very surprising result. Out of 27 hacked protocols, 14 of them has one single hacked transaction that introduces the only non-trivial control flow observed in the entire protocols, which means if we only allow users to invoke one function in one transaction, then we could already prevented 14 out of 27 hacks. It's more than the half with 0 false positive rate. The only experienced user of the protocol is a hacker, which is very interesting. And how can we enforce such a policy? Let me illustrate a simple example involving the previous illustrative example I used. The withdrawal function, in a binary transaction, the user calls the upper level contract, which in turn invokes a guard contract here. So when a user invokes a withdrawal function, at the start and the end of its execution, it's going to report the control flow to another smart contract, which is a guard contract, and it records, okay, now the control flow is withdraw start and withdraw end. It is one simple invocation, which is trivial, and we allow it. And for a hack transaction, the hacker first calls the deposit function, and it will be recorded as the deposit start and deposit end as a control flow inside the guard contract. At this point, it works. It's still allowed. It's a trivial control flow. Then the hacker can manipulate an external oracle, which triggers which is certainly external, and the DeFi protocol A cannot be aware of this. Finally, the hacker calls withdraw. Again, the DeFi protocol A will register the function call inside the guard protocol, the guard smart contract. Now the recorded control flow becomes deposit start, deposit end, withdraw start, and withdraw end, which is a non-trivial control flow, which means the control flow of that transaction actually deposit tokens and withdraw tokens in one single transaction, which is really abnormal. At this point, the guard contract can find, okay, this is a non-trivial control flow which we do not allow. Then the guard contract can immediately revert the transaction. But here also comes two main challenges of applying this system. The first one is false positives. Despite it may work perfectly well for some protocols, I mean, unavoidably we will meet some false positives, which means the transactions which are completely benign, but we revert it because we detect the non-trivial control flows. So here we introduce two policies to further reduce the false positive rate, which is runtime read only and restore on exit. So these two are two flags we track on the fly to record the properties of the execution. So for runtime read only, whenever we encounter an opcode which will alter the blockchain state, we will mark that flag as false. For restore on exit, we record, we store the storage slots that got changed and see if it's at the end gonna be reset back to its original value. In that case, we do not make it a non-runtime read only. A second challenge we encounter is a very potential high gas overhead. To reduce cost, we propose several optimizations, and the most effective one being the guard contract merging. So instead of deploying a separate guard contract, we can merge it with the most frequently used contract, converting all the external calls to internal ones, dramatically reducing the gas usage. If we cannot identify which contract is used the most often, we can use the contract with the largest binary size, because the more implementation logic usually means the more usage. The results are actually very encouraging. Even without training data as traced to inv, our CrossGuard system can successfully stop 35 out of 37 hacks. When trained with historical transaction data, in the similar setting as trace to inv, they can whitelist the non-binary control flows. We further reduce the faulty rate to just 0.15%. Finally, I'm going to propose the third line of defense. This is future work. We haven't done it, but we envision a systematic DeFi risk analysis framework that can continuously monitor inter-protocol independency risks before it got exploited. So again, if we look back to this graph, we find actually there are a few high risks in the whole DeFi world. If one collapses, the others could fail like dominoes. The first one is some very basic DeFi smart contracts are upgradable. For example, the most popular stablecoin contract, USDC, is upgradable, which means if one day it got hacked, I mean, all the other smart contracts using stablecoins could collapse. And the second one, the system has, well, if there's a scenario when the system has more claims on the asset, which is the top Legos of the top Legos smart contract, then real collateral supporting them, which is bottom Legos, then the system has a systematic risk. It can collapse overnight. And the third one is the DeFi Legos depend on each other. If one Lego breaks, the other collapse like dominoes. So our proposed, the third layer of the DeFi Lego is to constantly monitoring the whole ecosystem. Given a protocol A, we monitor their dependencies and also monitor the overall, the basic DeFi Legos, infrastructure Legos, to see if there's a potential risk behind it. So as a summary, we propose 3 layers for a dynamic security framework for DeFi smart contract. Thank you very much. I think that's the end of my presentation. Here are the references. Thank you.